Good afternoon. Welcome to Krishna's class. We continue with the proof of the Riesz representation theorem. We have already explored 3 steps and we are now going to take up the 4th step, which deals with the countable additivity of elements in MF. I mean mu on elements in MF. Now I have put down MF here. MF consists of all subsets of the space X with the measure of or the mu of E finite and mu of E equal to supremum of mu k contained in X where k is compact. This essentially means that all those E which can be approximated from within in the in terms of mu by compact sets. It's essentially this. This is your E, and now you have some compact sets K. So mu of K is as close as you want to the mu of. So we want to see what we have is this mu of K, where K is compact. So there are several compact sets inside E. Now what we want is the following. That is, all those E for which mu E can be approximated from within by K as closely as you want in terms of mu. This is what. Okay. So such E's are elements of MF. Of course, mu E is finite. So these are the two conditions that you have. Mu E is finite and this property is there, that mu E is as closely as you want, or given epsilon positive, there exists K compact, K contained in E, such that mu of K is so this is the quotient. Okay. So this property is valid for the sets E that we are now considering. We are only talking about properties of it. In fact, we proved that the mu that is defined for all subsets of X, right? And we have proved that in step 1 we explored and proved that we have step 1 mu is countably subadditive on Px. Px is the set of all subsets of X. That is what we did in this one. Now we are going to consider a subcollection of Px which we designate by M sub F, and for this collection we prove that mu is has a stronger property, namely that mu is countably additive. Okay, so that's our task, and we just also write in step 2. In steps 2 and 3, if V is open and mu of V is finite, then V belongs to. We are trying to get a idea of what sort of sets are there in MF. In fact, we find that the entire collection of open sets for which mu of V is finite belong to that is one thing, and the second thing is mu of K is finite. K belongs to K compact. So all compact sets have mu of K finite, and they all belong to this class. So in steps 2 and 3, we got an idea, or we are rather assured that MF consists of a huge class of subsets of X which are relevant to our discussion. Now we go to the step 4. So step 4, we prove that is countably additive. That is, if Pm consists of a collection of mutually disjoint sets, then mu of equal to in fact, you recall that in step 1 we proved that for all En in Px we have the property that this is less than or. So one part we have already proved. Okay, so what remains to be proved is that we already know that is less than or equal to so it remains to if is mutually disjoint then mu of n. So if we prove this, then these two put together would give you the quality. So that's our task. Okay, what do we do? How do we work on the proof? We first prove that for compact sets, for disjoint compact sets which are already in MF, that we know, okay, this property is satisfied. So we first show that mu of is equal to where K1, K2 compact in X and K1 intersection K2 . That's our first step. Once we prove this, we can extend the finite collection of Ki's and then to the countable collection. Of Ki's. Then after that, we take it up for all elements in F. Because one of the properties of elements in MF are that they can be approximated from within by compact sets. That's the reason why this works. Okay? So that's the crucial property that identifies sets in MF. So we will exploit that. So what we do is, assume compact subsets and K1 union K2 belongs to M. And this is of course the crucial condition that is required for this. If that condition is dropped, once again only subadditivity is valid. So choose epsilon constant. By Urysohn's lemma, lemma, there exists f belonging to CCX such that f of x equal to 1 on K1 and K2 and what? So this property is satisfied. So this is what you have. You have K1, you have K2. Now this is your x. So by K1 is compact. Now you see that K2 complement is open. Okay. So note that and K1 is contained in that this property assures that this is so. So K1 is a compact set, K2 complement is an open set, and therefore by applying Urysohn's lemma, by Urysohn, there exists f belonging to CCX such that K1 is subordinate to f is subordinate to K2 complement. Okay, and naturally you have. So my statement is now substantiated. Why you have such an okay? Now we work on this f and build our inequality. Now by step 2, there exists a G such that K1 union K2 is subordinate to G. That is simple because K1 union K2 is a compact set. Okay. Therefore, this is one part of this system. You have such a G and K1 union K2 subordinate to G. G. This means that Gx equal to 1 for every K2. So that property is satisfied. Further, lambda G, that is the given linear functional, is less than mu of K2 plus etc. Now this follows from step 2, right? Because you see that mu of K1, K2 is the infimum of all lambda G, okay, where this property is satisfied, right? because that is the reason. This property is success. Now, so we have got a G now. So we have got an F which is identically equal to 1 on K1. Now, K1 because you see that G is also equal to 1 on both K1 and K2. Therefore, on K1, Fg equal to 1. So, on okay, and this property, the other property follows from properties of Fg, right? And K2 on K2, you see that this is equal to 1. Okay, because on K1, this is going to be 1 minus F is equal to 1, this is 0. Okay. On K2, what happens is that F is equal to 0 on K2. Therefore, this is K2 on K2. This becomes simply G, and G by our choice is equal to 1. Okay. Therefore, now and hence mu of is less than or equal to lambda of Fg plus lambda of 1 minus Fg, because you see that Fg plus 1 minus Fg is essentially G. Okay, so this is going to be mu K1 plus mu K2. This is mu K1, this is mu K2. I mean, this would, from this you would get mu K1 and K2, and this is equal to lambda of G. That is what I was telling. This, because of the linearity, this is equal to lambda G, because Fg plus 1 minus F into G is essentially a breakup of G. Okay, and this is less than mu of H. So what have we got? We have got mu K1 plus mu K2 is less than or equal to mu K1 plus K2 plus epsilon for any epsilon. What does this mean? This implies epsilon being arbitrary, mu of and then with the other inequality that I have mentioned at the beginning, okay, together we get subadditivity mu we obtain Now we look at various scenarios. First we consider, suppose E of E equal to E. Then the first inequality is automatically satisfied, and this one of course tells you that this is infinity, this is anyway satisfied, and the other one also is available we have, and therefore so we already have this is subadditivity property. It follows that mu of E is equal to sigma Of course, this is not required in this argument, but this is what you have. If E where E is equal to now in this case, that is where mu of E is infinite, then it immediately follows that mu of E is equal to this. So that is rather trivial. So we have to now assume that mu is finite, and then see we are now not working on compact sets, but we are now working on ENs which are in MF. Okay. Assume it is joined disjoint E equal to E, mu of E is so this is the scenario that we are considered already. the case where mu of E is EI HI such that mu of HI is greater than mu of EI minus 2 to the power minus I. This is possible, okay, because EI is contained in HI. So what you are saying is that mu of EI is less than mu of HI plus 2 to the power minus I. Okay. Put now these are mutually discharged. By induction, you see that mu of Kn is equal to mu of H1 plus mu of H2 plus etc. mu of H. That is clear. That is the extension of this idea. Okay. Therefore, by induction you have mu of E is greater than or equal to mu of Kn is equal to sigma I equal to 1 to n mu of Hi which is greater than sigma mu of Ei minus H. So you have mu of E is greater than or equal to sigma mu of Ei. For every n. This is true for every. So if mu of E is finite, and epsilon positive, then we have some routine arguments that you the sophistication of thought. You have mu of E less than or equal to epsilon for some n. Hence, mu of E is it follows that mu of E is less than or equal to Kn plus 2h. Kn is union of H1, H2, etc. Okay, and that implies E satisfies supremum of mu of K, where K is contained in E and K compact. This is satisfied. Okay, it follows from. And that, of course, implies E belongs to okay, and mu of E is equal to sigma K equal to or N equal to 1 to infinity mu Ek or En. Now, so that actually completes our countable subadditivity. Additive, not subadditive, on this is what we wanted to. Okay, right. Now we can immediately obtain another useful inequality. That, see, we were making a statement that, see, what we can show is that if E is an element of MF, then can approximate it from within to see a compact set. Already you can approximate it from outside with open sets. Now, what the next property tells you is that you can choose an open set which contains the given E and a compact set K which is contained in the given open sets, such that the mu of V and mu of K, okay, they are arbitrarily close to mu of one from below and the other from above. This is what we have. This is E. Then you have a particular K. So you have a K. This is your K, compact set. And then you have an open set V. This is V. So that what you have is this, that is mu of E is okay. Less than epsilon. And you see that this is essentially squeezed between these two. Okay? Right. So mu of K is nearly equal to mu of, or the supremum of mu of K would be mu of E, and the infimum of mu of V is equal to mu of. So these are the two results that you have. We prove that supremum of which is equal to infimum of mu of V, where E is contained in V open. So this is the approximation by compact sets from within and open sets from outside. Now this result is contained in next step. If E and epsilon is positive, then there exists a compact set and an open set V containing such that K is contained in V, and mu of V minus K. See, K is contained in V is less than. This is the statement of set. Let's prove it. Now the proof is very simple. Definition of implies there exists a compact set K contained in V and open set V containing V such that it comes from the fact that this is the supremum and infimum. See this statement. This is the one that I am referring to. Mu of V minus epsilon by 2 is less than mu of V less than mu of K plus epsilon. So K lies as closely as you want to E, so that when you take mu K and exceed it by epsilon by 2, then mu E becomes something less than that. And so also mu V you take and lessen it by epsilon by 2, then mu E becomes more than that. Okay, so that comes from the supremum and infimum definition or the infimum properties of mu of E. This is mu of E. Okay, since K is compact, so therefore, and K is contained in V, therefore V minus K is open. Already V is open. V minus K, because then all that you need is mu of V minus K should be less than mu of V minus K should be finite. So that property is satisfied. Because of this inequality, it immediately follows. Okay. Hence, by step 4, which we have just now proved, that is additivity, you see that this is what you have: K union V minus K. This is equal to Q. Sorry, this is equal to V. Therefore, see that therefore you have mu of because these are disjoint. Okay, so you have K intersection V minus K. That is the reason. And you see that mu V is less than epsilon. Now combine these two. Okay, consequently, mu of V minus K is less than. That means you can approximate from outside through an open set and from inside through a compact set, such that the mu of V minus K becomes as small as you. So this is a result that would be useful in proving the later part of this theorem. I think I will wind up here for the day. Okay, and we will continue with the further steps of this proof in our next. So, thank you very much.